In this video, we'll be looking at solving of questions. So chemical process calculations to just solving of questions. So now our first question is a cylinder fitted with a movable piston. So from our previous video, we looked at closed systems and then open systems. So now in this video, we'll just be solving questions on both open systems and then closed systems. An amount of 8.3 kilojoules of heat is transferred to the gas so that we can draw our cylinder. So this is our cylinder with a piston. An amount of 8.3 kilojoules of heat is transferred to the gas. So we have our heat source here, an amount of 8.3 kilojoules. And because heat is being transferred, then our heat here is positive 8.3 kilojoules. To raise the temperature of the gas 100 degrees Celsius higher, so our change in temperature becomes 100 degrees Celsius. We are raising it 100 degrees Celsius higher. So if initially the temperature was, let's say, 20 degrees Celsius, then 100 degrees higher will make the final temperature to be 120, right? And that will make the change in temperature to be 100 degrees Celsius. The gas does 68 joules of work in moving the piston to its new equilibrium position. So now the system does work. When you see a system is anything under consideration or anything under discussion. Now in this case, our gas becomes our system, and then it does 68 joules of work. Now the gas, so in actual sense, this is what it means. The gas expands and it moves the piston up to another new position, right? So this is the gas that expands. So let's say previously it was filled to this volume and it has expanded to this volume. And then it does so by doing a work of 68 joules. Then there is a heat of 8.3 kilojoules. Now let's ask ourselves, is this a closed system or an open system? Well, we have a piston here, so that means it's a closed system. We've discussed about this in our previous video. Now we just have to go back to our first law of thermodynamics for a closed system. The gas does 68 joules of work, so the system does work, right? So that becomes positive. So our first law of thermodynamics is Q minus Ws is equal to change in U plus change in kinetic energy plus change in potential energy. Kinetic energy and potential energy, we didn't have much information on that, so it's 0. So Q minus Ws is equal to change in U. We know change in U to be our internal energy. This is our work, shaft work, which is the work done by the system, and then our Q is our heat. Q is positive, right? So 8.3 kilojoules minus our work is also positive, so minus positive 6.8 joules. It's equal to change in U. Now we can only add like things. This is in joules, this is in kilojoules. So before you can even add or subtract them, you have to convert them into one single unit, right? So I prefer you convert the joules into kilojoules. So we get 8.3 kilojoules minus 6.8 divided by 1000 kilojoules, right? So the whole idea is that when you have joules and want to convert it to kilojoules, you know kilo is a prefix, which is 1000. So you can see you are going to multiply both sides by 1000. And this implies that we've actually done nothing to the equation, to the expression here, because this and this gives us 1. But then we replace this with a kilo, and then this comes over 1000. That's why you're dividing by 1000. And then we are going to get 8.3 kilojoules minus. So this is going to move the decimal place 3 times. So 0.123, 0.005, 0.0068 kilojoules is equal to change in U. Now change in internal energy becomes 8.3 minus 0.0068. Then we get 8.2932 kilojoules. Now this becomes our internal energy. So let's quickly move on to the next question. So the next question says that a steam flowing at a rate of 10 kg per hour so enters a steam turbine. So we can just do a sketch of our steam turbine. So if this is our turbine, and then the steam So I have our steam here flowing at a rate, we'll read the math rate of the inlet, 10 kilogram per hour, enters a steam turbine at a velocity of 50 meter per second. So VI entry 50 meter per second, and leaves at a point 5 meters below the inlet. So that means if this we are choosing this as our inlet, then our outlet will be -5 here because it's 5 meters below. We can even get rid of the negative and just see that just 5 meters below. Right. So in our head, we know that it's below this. So if you are choosing this to be our reference, this will be below that. Below the inlet at a velocity of, now it becomes V2, 300 meter per second. The heat loss from the turbine is estimated to be 10 kilowatts. Now the turbine loses heat, 10 kilowatts. Of course, heat loss from the system is negative. And the turbine delivers shaft work at a rate of, now the turbine does work 70 kilowatts, and that is positive. Right. Calculate the change in enthalpy transport rate of the process. So now let's ask ourselves, is this an open system or a closed system? Well, we have our mass flow rate here, 10 kilogram per hour, so it's an open system. And besides, we still have a turbine here, which makes it an open system. Now let's look at our unit very well. This is in kilowatt, and this is also in kilowatt. What is joules per time? To be specific, joules per second is watt, right? Now let's write our first law of thermodynamics for an open system, because you have to do our energy balance. Q minus shaft work is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. The moment they give you velocity, then you should know that your kinetic energy isn't negligible. Unless, of course, the question still states that neglecting kinetic energy. If not, you have to include it. Sometimes the question will be in this form: neglect the kinetic energy of the outlet stream. That means you still have to include the kinetic energy of the inlet stream. Just that the outlet stream will be 0. And then for the potential energy, the anytime you see that there is a change in the elevation of the system, so probably the inlet stream is at a higher elevation than the outlet stream, or the inverse of that, then you should know that you have to include potential energy. It's not negligible. Now let's come back to our equation. Let's find our terms separately, and then we can just put it into the equation. Our Q is -10 kilowatt. Our WS is 70 kilowatts, right? So let's evaluate our kinetic energy. It's better you solve them separately. You know kinetic energy is supposed to be half mv squared. So far as you are looking at the change, you are going to do v2 squared minus half m v1 squared. Now let's take note of something. I want us to clarify certain things here. The moment you have our turbine, right, the first thing you have to do is that you have to do material and energy balance. I didn't talk about the material balance because I know you did it in the previous semester. So with the material energy balance, it means that all the streams entering, their mass flow should be the same. Right? So if this M1, M2, M2, then M1 is equal to M2 plus M3. But then from this question, we have just one inlet stream and then one outlet stream. So our M1 is equal to our M2, right? That's why I used M in both cases. But the actual thing is supposed to be half M2 V2 squared, which is the outlet, minus half M1 V1 squared. Now because M1 is equal to M2, then we can say they are both equal to M. And then we will say that change in kinetic energy is equal to half, you can even bring the M out, V2 squared minus V1 squared. And then our M becomes our flow rate. So let's evaluate that. But then I want us to clarify certain things here. So now, let's evaluate only this part and see. V squared, right, is actually equal to, V is meter per second. So we are squaring this. And this is meter squared per second squared. So what's the derived unit for meter squared per second squared? So now we'll come here and see that work is equal to force times distance. And then the unit is in joules, right? Force is mass times acceleration, so kilogram meter per second squared times distance m. So the whole of this is our force, and this is our distance m. So we get kilogram meter squared per second squared, and that is joules, because that is work done. So it means that kilogram meter squared per second squared is equal to joules. So now when we want just meter squared per second squared, I'm going to get meter squared per second squared is equal to joules per kilogram, right? So it means that when we evaluate only v squared, v2 squared minus v1 squared, our unit here becomes joules per kilogram, right? Now when this is given as joules per kilogram, the 2 is a constant, right? So dimensionless. So we are still going to get joules per kilogram. But then when you multiply by the mass flow rate, because the mass flow rate is in kilogram per, from the question, the mass flow rate is in kilogram per hour. When you multiply these two, to joules per kilogram times kilogram per hour, kilogram cancels kilogram, you need to get joules per hour. Now let's take note. Joules per hour isn't equal to what? Right? It's supposed to be joules per second. That's what I want. So you have to convert this into joules per the hour to joules per second. And then to simplify things, we would rather convert the mass flow rate into kilogram per second rather. So that when you multiply by this, you can just get joules per second, and that would be our watts. And you can just put it in the equation. And you should also take note, our W and our Q are in kilo, but this is in watt. So you have to divide by 1000 to get it in kilowatts. So I think if we understand this, you can just go ahead and then do the calculation. So first of all, one thing we realize is that, sorry, so let me clarify something here too. So our kinetic energy change becomes m, you can make our m out and see v2 squared minus v1 squared all over 2, right? And our potential energy change is also, it also follows the same procedure, m2 gh2 minus m1 gh1. So now m1 and m2 are the same, so we can just factorize our m out and see it's m out, g is also out because g is constant, h2 minus h1. Right. Our m is our mass flow rate, and this m is the same as the m for the kinetic energy. And then our change in enthalpy here too, it depends on the unit we want. So mostly in some books they use small h to represent a specific enthalpy, so kilojoules per kilogram. And then when they're using a capital H, it's actually the enthalpy rate. So let's say kilowatts. But then if you understand what you are doing, I think using the whether capital or small letter doesn't really matter, right? So now because our potential energy here is mg changing h, right? And you can factorize our m out. And then for our kinetic energy, so we can factorize our m out. Now realize that when you factorize our m out from the kinetic energy, we get, so here when we excluded the m, we had meter squared per second squared, and that was kilojoule per kilogram, right? Or joules per kilogram. So it means that we can factorize our m out from the whole equation. So our Q minus Ws now becomes m out, change in enthalpy, plus change in kinetic energy, plus change in potential energy. Let me use a small letter. So I'm using a small letter because we factorize the mass flow rate out. So it means that everything we have here is actually in joules per kilogram, specific. Good. So now our enthalpy here will have a unit of joules per kilogram. This will also have a unit of joules per kilogram. We also have a unit of joules per kilogram. And then we've settled the kinetic energy one. So I will probably do the potential energy one so that we'll clarify things. So with the kinetic energy, now I think the kinetic energy becomes just half v2 squared minus v1 squared. Right? We factorize our m out. So let's just put in the values. And then we know that v2 squared minus v1 squared will have a unit of joules per kilogram. Because from here, v squared is meter squared per second squared, and that is joules per kilogram. So we have v2 Our final velocity was 300. So 300 squared minus 50 squared. So change in kinetic energy becomes half times 300 squared minus 50 squared. So we get 43750 joules per kilogram. Now, our K and W here are in kilowatts. So if our kinetic energy is in joules per kilogram, then when you multiply it by our mass fluids, our mass fluid is in kilogram per second, right? We'll convert it in kilogram per second, but from the question it was kilogram per hour. You shouldn't worry about that. We'll convert it to kilogram per second. So when we multiply this by our joules per kilogram, we're going to get joules per second, which is watts. And then that wouldn't be dimensionally feasible with this because this is in kilowatt. So straight away you have to divide by 1000, right? So 1, 2, 3 to get 43.75 kilojoules per kilogram. So we can draw a conclusion here, right? The one thing you should take note is that the calculations are always the same. So our conclusion here will be that change in kinetic energy will be half V2 squared minus V1 squared all over 1000. Now when you do this, your unit then becomes kilojoules per kilogram, unless you multiply this by your mass fluid. If you multiply this by your mass fluid, then you are going to get kilowatts because your mass fluid will be in kilogram per second. If not, we stick to this kilojoule per kilogram. So that's what we are doing because you factorize our mass fluid out. So we haven't multiplied this by our kinetic energy yet. So the answer now becomes, change kinetic energy now becomes 43.75 kilojoules per kilogram. So let's go to our potential energy. It's also the same thing. We factorize our M out. So now you just have G H2 minus H1. So now let's do the dimension analysis. G is acceleration due to gravity, meter per second squared. Our H is also in meters. Now we get meter squared per second squared, and which is joules per kilogram from what we've done here, right? Good. So now our change in potential energy now becomes our G. So if we are taking G to be 9.8, 9.8, H2. Now H2 was 5 meters below H1. So we can see that if we are choosing our H2, our outlet stream to be our reference, that means this is the zero line. This is above it. So now this becomes 5 meters from that. Now H2 is 0. Our H1 becomes 5. When you do that, you're going to get 9.8 times negative 5. And our change in potential energy becomes 9.8 times negative 5. You get negative 49. Take note, your unit will be in joules per kilogram. Now, because you want to convert it into kilojoules per kilogram, I'm going to divide by 1000, and then we get our change in potential energy to be 0.0. So you are moving 3, 1, 2, 3, negative 0.049, right? 49 kilojoules per kilogram. So change in potential energy is equal to negative 0.049 kilojoules per kilogram. So I want us to clean these parts so I can get more space and work with. Good. So now we know that our mass fluid, right, was given as 10 kilogram per hour. Now, because you want to convert everything into kilowatts, you have to convert this into kilogram per second. Right? So we do our conversion. 1 hour is 3,600 seconds. So our mass flow rate then becomes 10 over 3,600. So we get 2.778 kilogram per second. So R cancels R. Right? Now mass flow rate is 2.778 kilogram per second. Right? So putting everything into the general equation, this you are going to get R Q is negative 10, our WS is 70. Right? So they are all in kilo because now we see that we factor our mass flow rate out to 2.778. Change in enthalpy plus change in kinetic energy was 43.75 minus our potential energy is negative, so negative 0.049. So you divide through by 2.778. Right? You divide through by that. Now because this is in kilogram per second and then this is in kilowatt, which is joules, kilojoules per second. When you divide by that, then it becomes something like this: second by kilogram. So seconds can to second. We are left with kilojoules per kilogram. And then this are also in kilojoules per kilogram. Kilojoules per kilogram. And then you can subtract easily. So we divide 2 by that. 2.778. Sorry, I made a mistake here. So now this is 2.778 times 10 to the power negative 3 kilogram per second. So let me put it here, times 10 to the power negative 3 times 10 to the power negative 3. 2.778 times 10 to the power negative 3. This divides this. So now negative 10 minus 70 divided by 2 point, we get negative 28800. So our unit here is kilojoules per kilogram. The entire the same unit as it is. So we change the enthalpy plus 43.75 minus 0.049. So when we solving this, we can get our change in enthalpy to be, that would be negative 28800 minus 43.75 plus 0.049. So then we get negative 28843.701. What will be the unit of this enthalpy? To be in kilojoules per kilogram. But the question says you should find a rate, right? So we know that rate is what? Per second or per time. We have to multiply this by the flow rate. So our capital H becomes M times change in small h. And our M was in 2.778 times 10 to the power negative 3. So we have to multiply that negative 28843.7. And then our answer becomes 2.778 times 10 to the power minus 3 multiplying negative 28843.7. Now we get negative 80.13. Right. Okay, I still have to clean. We'll be solving more questions, so that's why I wanted us to understand how the unit conversion and everything will be. That in our subsequent questions, we'll just be writing the equation and then putting the values. So now our change in enthalpy becomes negative 80.13. So what will be the unit of this? The unit of this will be in kilojoules per second, and that is our kilowatt, right? Because our mass flow rate is in kilogram per second, and our enthalpy was in kilojoules per kilogram. So this cancels this. I left it kilojoule per second, which is in kilowatt. So therefore, our change in enthalpy becomes negative 80.13 kilowatts. So let's move on to the next question. So our next question is the specific internal energy of helium at, so now you have helium at temperature of 25 degrees Celsius, and that is equivalent to 298 Kelvin, and a pressure of 1 atm is 3.8 kilojoules per mole. So specific internal energy. Right? Note, this isn't change in internal energy. They said just internal energy. So U 3.8 kilojoules per mole. And a specific molar volume under the same conditions. So you have our volume, it's specific. Some they use this at sign, 25 liter per mole. You should take note that liter is the same as decimeter cube. Right? So you can just write 25 decimeter cube per mole. That is our volume, specific volume. Calculate the specific enthalpy of helium at this temperature and pressure, and the rate at which enthalpy is transported by a stream with a molar flow rate of this. Now, when we see specific enthalpy, what it tells us that it's specific. When you say specific, something per kilogram or per mole. So our enthalpy, you are going to have it two ways. The small one, which is to be in kilojoules per mole here, and then the actual transport rate, which will be in kilojoules per second or kilojoules per hour, depending on what we want to work with. So now, someone can see that because of the flow rate, it's an open system. Yes, it's an open system, but then the question doesn't really stress much on whether it's so open or it's closed in relevant solving the question, right? So we just want to find our enthalpy, right? And we give it the internal energy. Besides, the internal energy wasn't stated whether it was in or out, right? So what we know is that enthalpy, right, is equal to U plus PV. So it is our use internal energy, whether it's in or out, we don't care. And our PV here is just pressure and then our volume. Our U here is, from the question, is 3.8 kilojoules per mole. Our PV here, when you multiply them, we should also get kilojoules per mole so that we can add them. Now we know that pressure times volume actually gives us joules, right? That's why the volume here is specific, so per mole. So you can get joules per mole, and then we can convert this to kilojoules per mole, and then you can add them. Now, what makes pressure times volume give us joules? The pressure is supposed to be in Pascal, and the volume is supposed to be in meter cube. So therefore, meter cube Pascal is what is joules in the derived unit. So let's take note of this. Now, our pressure that we have here. So now, if our volume is specific, so meter cube per mole, we are going to get joules per mole, right? And then our pressure here is 1 atm. So we have to convert it into Pascal, right? So you are just going to do a simple one. I don't know if I should just multiply them before converting them. So I'll just multiply them. So pressure times volume here is 1 atm times our volume, which is 25 liters per mole. So 25, I prefer using the meter cube per mole. So you are going to get 25 atm dm cube mole. This. So we have to convert our pressure to Pascal, decimeter cube to meter cube, right? So 25 atm decimeter cube per mole. So our mole will be still fixed. Right? Now let's convert. So we have millimeters, centimeters, decimeters, and meters. Right? So remove one. So 1 meter is equivalent to 10 decimeter. But we want the cube, so we just have to cube both sides. And then we are going to get 1 meter cube is equal to 10 to the power 3 dm cube, right? So this is the way I used to derive the conversion factors. And then atm, so 1 atm is equivalent to 1.01325 times 10 to the power 5 Pascal, right? So now our pressure times our volume that we have here, atm divides atm, dm cube divides dm cube. So you are left with 25 meter cube times 1.01325 times 10 to the power 5 Pascal all over moles times 10 to the power 3. Yes. So now meter cube and a Pascal will be giving us our joules. So we are going to get 25 times 1.01325 times 10 to the power 5. So we have our joules here. And then 10 to the power 3, we have our mole. So we have to evaluate this. So we get our PV to 25 times 1.01325 times 10 to the power 5 divided by 10 to the power 3. So we get 2533.125 joules per mole. Right. Now I want to convert this into kilojoules per mole because our U here is in kilojoules per mole. We just have to divide through by 1000. And then our PV becomes 123, so 2.533 kilojoules per mole. So now our H is now 3.8 plus 2.533. Now you get 3.8 plus 2.533. We get 6.33 kilojoules per mole. Now this enthalpy we found here is actually specific, right? So that's why I say that when some books they use small letters to represent the specific and capital letters, but then if you know what you are doing, so I used capital H for my specific. So 6.33 kilojoules per mole. So I just see that my enthalpy rate, right? So I just use the small h for the rate. It's equal to the molar flow rate times the actual enthalpy. Because this is in per mole, I can multiply it by kilogram per hour. So it's supposed to be kilomoles per hour, and that's what the question gives. So 250 kilomoles per hour times 6.33 kilojoules per mole. Right. Now the mole divides mole. We are left with kilo. So we have 10 to the power 3 here. And this is in per hour, right? So let me clean this space and then let's make use of it. So now we have 250 times 10 to the power 3 times 6.33 kilojoules all over R, right? So 250 times 10 to the power 3 multiplying 6.33, right? So we get a very huge number, which is 1582500 kilojoules per hour. So now let's try converting it to kilojoules per second. So 1 hour is 3600 seconds. R cancels R, and then we are left with 1582500 kilojoules over 3600 seconds. And then we get 439.58 kilojoules per second. And that's equivalent to 439.58 kilowatts. So that will be all for now. So our next video will be looking at using steam tables for open systems too. But then before that, we have to introduce how to read the steam tables and all. Thanks for your time.